lie. Why is that a lie? Per equals never works. It is truthful. But if you say that when temperature in Kelvin goes to 0, the volume of the gas goes to 0, you're lying. Why are you lying? Because what? Yeah. Don't the molecules still exist? Don't those molecules take up space? Okay. When temperature goes to 0, are the molecules vibrating? No. So they're not taking up extra space. You follow? The V in PV equals nRT is actually the extra space occupied by the movement of the molecules relative to all the other movements, and they need more space to exist because they're vibrating. Everybody get that part? And in comparison to the amount that they move and vibrate compared to the volume of the molecule itself, the molecule doesn't have volume. That volume of an atom is so small, we don't care, compared to its macro volume of the fact that when it's moving at 30,000 meters per second, in some fraction of a second it takes to collide with somewhere, it went a pretty big distance. That makes sense that way? Okay, so temperature represents the average kinetic energy of the molecules. And that's whether it's a gas, a solid, anything. All right? Oh, come on. All right. Objective. So understand Celsius, Kelvin, Fahrenheit scales, go in between them. And we're also going to deal with some things on linear expansion. All right. Thermal energy. And this isn't quite heat yet. When we do heat, heat's going to get the letter Q. All right? Thermal energy. All of the thermal energy. So I have U. That's total internal energy. Where does that come from? Total internal energy comes from how fast the molecules of that system are vibrating. The K, the kinetic energy, is how fast the molecule is moving macroly. Such as when I have my tennis ball over here. Does this have thermal internal energy? Sure, because if I put this in ice, wouldn't it melt the ice? I don't have to have this moving to melt the ice, because the ice would try to raise in temperature, this would be cooling down, and the fact that this is going from a high temperature to a low temperature, that would be an amount of heat that I'm transferring to the ice, right? And that thermal energy, that stored energy, that's the U, potential energy, right? That's due just to the fact that the molecules that make this up are moving, they're vibrating. But relatively to this unit of space in our room, is the tennis ball moving anywhere? No. So I'm saying it has my potential energy, but it does not have kinetic energy, because I don't have movement of that, right? And so the total energy available is just potential plus kinetic, because there are only two types of energy, which we're going to get to later. So we get that in November or December. I don't know when. But energy, just like with forces, how many types of forces are there? Two, contact and field. Everything's a contact or a field force. All right? Energy is either potential or kinetic. Now, there's a bunch of forms of potential energy, and it all deals with position and that vibration and everything else. So internal energy, the springs, when it vibrates, because I can store energy in a spring, right? You know, you can store energy in a rubber band by stretching it. That's the potential. Okay. Average, here we go. A good beginning to define temperature. It's the average kinetic energy per molecule. So if I take the sum of all the kinetic energies and divide by the number of molecules that I have that have all that kinetic energy, internal, stored, potential kinetic, vibrational energy, all right, that's where I get temperature from. Isn't temperature a whole lot easier to think of, though? Okay, and that's why we use temperature. All right, temperature versus internal energy. They have this picture, but I'm going to do it this way. Which has more thermal energy? A a gallon of boiling hot coffee or Lake Arlington? Lake Arlington by probably factors of millions or more. All right? Because if I took that gallon of boiling coffee and I poured it into Lake Arlington, would the whole temperature of Lake Arlington raise? Like nothing. Because it's so large, right? And what's the Kelvin temperature of Lake Arlington? Maybe 300, right? Remember, 0 is 273. So 0 Celsius would be 273, and it's not 273, right? So let's say like 300. But I have, how many meters cubed is Lake Arlington? It's a lot. And I have from 300 to 0 worth of energy, right? For my gallon of boiling coffee, what's my temperature change down to 0? Well, it's 373. But it's only 1 gallon compared to all of Lake Arlington, right? So my 1 gallon gets 373 change, but each gallon of Lake Arlington would get 300 down to 0. So Lake Arlington has a lot more thermal energy, even though it's colder. So temperature and thermal energy, the energy are two different things. That's what I want to make sure. Okay. Temperature equilibrium. This deals with what is the transitive property? Math. I know. You all think chemistry. What's the science transitive property? I don't know. They never told me. No, I'm just math, okay? Transitive property.
A equals B.
B equals C. Then, thank you.
Come on, y'all know that.
Yeah, did everybody sign? Okay. So one of the things that's going to happen, thermal equilibrium. All right. Your body is a fairly good temperature gauge. Can't you tell when things are hot or things are cold? And can't you use your hand to do that? So wave your hand, get an idea of the temperature in this room, because I think it's pretty warm in this room. Right? Okay, now again, put your hand flat on the table. Okay, which one's hotter? The room or the table? The room? Y'all are idiots. I'll say that nicely. How long do you think these tables have been in this room? Okay, long time? Yes? All right, thermal equilibrium, this is what's going to happen. If something is at a higher temperature, if object A is in thermal contact with object B, and if object A is at a higher temperature than object B, it will transfer energy to B until they reach the same temperature. Because temperature is average kinetic energy. And if one is banging around really a lot, and the other one's just going, ooh, when the one that bangs it hits it, don't those molecules start to move faster? And all the molecules move equally when the temperature is the same. So things go from high temperature and give energy to low temperature. Now the amount of transfer of that energy is heat. But temperature, energy transfers from hot to cold. Now, isn't the air in this room and the temperature of the tables the same temperature? And yet every single one of you went, oh, the table's cold. Well, you did. I know. Okay. Why? Now, because what I want you to be able to do is, what are the consequences? It's okay to make an assumption. You make a guess. What are the consequences of that guess? All right. But now you got to think about, why did you think the table was colder than the air? Well, relative to your hand, the difference between the temperature in the air and the temperature of the table is the same. Right? Because your hand is probably about, the skin in your hand is probably about, in Fahrenheit, 96, 95, 94 degrees. Right? The table's probably about, although it's hot in here, so the table's probably about 76 degrees. The air's about 76 degrees. So the difference between your hand and the air and your hand and the table is the same. Why is the table cold? Because what? No. But that's an idea. Yes. And it's because of, there need another word in your thought there. It's because of how we biologically determine the temperature. If we are absorbing energy, we think it's hot. If we are giving away energy, we think it's cold. The faster we absorb or the faster we give away, the hotter, the colder that it is. So the table is a heat sink. The table, because of the material, is a solid, not a gas, because there are lots of molecules, so we're going to agree with that. The table draws energy from your hand quickly. Therefore, it feels cold. If it's cold outside, what do? Put on a jacket. What's the purpose of the jacket?
Keep the energy in.
To trap a layer of air that doesn't move next to your body. Why is it when it's hot you turn a fan on?
To disperse the energy.
Because your body heats up the air next to it. If there's no breeze, it stays hot. Right? Doesn't give off. It's hot. I'm absorbing energy, not giving it away. So what do? We blow air by it. So I can give off energy and I feel cooler. You follow the difference between the biological understanding now of what your body thinks it does or thinks it knows, and what physics does and thinks it knows? And I want to make sure that you can do the difference between them. Because you want to answer questions from the physics or physics land perspective. That's going to be important. All right, heat is the transfer of thermal energy. By the way, you are seeing these like the first time I get to see them. So I know all the things that I need to talk about, and I'm hoping that these have nice pictures. Thermal equilibrium, if and only if they have the same temperature. So heat transfer of energy, and energy will transfer from hot to cold. All right? So what's the temperature of your refrigerator? How about cold? I mean, you can give me a temperature, that's fine. What's the temperature of your house? Warm. Where's your refrigerator? In your house. So that means energy's going from cold to hot? How do you do that? That's not fair. But it must. If you think about it, if you think the refrigerator's cold, right? And it stays cold, and matter of fact, the freezer is even colder, right? And yet it's in the hot house. How does it do that? Well, I got PV present RT, right? If I compress the gas, right? I raise the pressure of the gas, I'm going to reduce the volume, but I'm going to do work on it. I'm going to compress the gas. What happens to the temperature? All right, if you ever didn't know, how about this one? How many of you ride a bicycle? Okay, have you ever let air out of the tire in a bicycle? Put your thumbnail on the little stem and let the air out. All right. What happens to your thumb? What happens?
Cold.
Why is it cold? If I keep doing this, right? It gets cold, yes? I can get really, really cold because you can get a freezer. You can burn with this, particularly if you turn it upside down so that liquid comes out. Okay? But now what's happened to the can?
It's cold.
Why? We just did both halves of what a refrigerator does. Okay? I take gas, which in the old refrigerators was Freon.